A rocky planet 48 light-years away is bleeding helium into the void of space a little bit every second, and has been doing so for more than 3 billion years without yet exhausting its atmosphere. And no one expected that a rocky world orbiting a star so fierce and violent could hold on to its air for so long. Stay with me because I am about to walk you through what scientists have just confirmed about LHS 1140b. And hit subscribe right now because this channel analyzes real space discoveries without the hype. And you do not want to miss what else is emerging from this planetary system. Because to understand why this week's discovery has left the entire astrophysics community stunned enough to rewrite assumptions that had sat undisturbed for 2 decades, we have to go back exactly 20 years, to the moment when science was certain this was impossible. Because the history of how we have viewed red dwarf stars is stranger than most people remember. For nearly 2 decades, science built a story that everyone following the exoplanet field knew, a rule quietly reinforced with every new observation until it became something no one needed to say out loud anymore. That story began with a simple observation about the nature of red dwarfs. They are not like the sun. They are smaller, dimmer, cooler, but for most of their lives they are unimaginably fierce stars, blasting out stellar winds dozens of times stronger than the sun's, erupting in unpredictable X-ray flares, and pouring out ultraviolet radiation at intensities that strip away anything that comes too close. And the problem is that every rocky planet known to orbit them has to get very close, because the habitable zone of a red dwarf sits right next to the star. Every time the James Webb Space Telescope was pointed at a rocky planet around a red dwarf in search of an atmosphere, the results came back nearly identical. Empty spectra, no sign of water vapor, no carbon dioxide, no nitrogen, nothing at all, just a bare rock illuminated by a red star. The most painful example is the TRAPPIST-1 system, one of the most intensively studied targets in the history of astrophysics, a red dwarf with 7 rocky planets around it, 3 of them sitting right in the habitable zone. Everyone thought that if there was anywhere outside the solar system that could harbor life, TRAPPIST-1 had to be the leading candidate. But when Laura Kreidberg and her team published the results on TRAPPIST-1b in 2023, the conclusion was no significant atmosphere. When Sebastian Ziba worked on TRAPPIST-1c that same year, the same conclusion. When Thomas Green returned to TRAPPIST-1b again, the same conclusion. Paper after paper, year after year, planet after planet, all led the community to the same answer. A cognitive tragedy began to take shape from there. Red dwarfs make up the majority of the stellar population in the Milky Way, and from an observational standpoint, they are the easiest targets, because they are so faint that they do not overwhelm their planets the way brighter stars usually do. But precisely because of their extreme activity, they gradually slip to the bottom of the list of potentially habitable systems. And the community gradually arrived at a conclusion that was never written down as official doctrine, but that everyone tacitly agreed upon. Red dwarfs are atmosphere killers. By the mid-2020s, the exoplanet community had reached something close to an unvoted consensus. The habitable zone of a red dwarf had become a formal term, a scientific label retained out of habit rather than any serious biological meaning. If you wanted to look for life somewhere outside the solar system, look for stars more like the sun. That was what everyone following the field knew without anyone needing to say it again. For a long time, that felt like the end of the story. Red dwarfs are small, common, easy to observe, and seemingly completely hopeless for life. It is also worth pausing for a moment to see clearly how little we actually knew about what that assumption was really based on, because there was one crucial thing the community had never truly tested. Throughout nearly 2 decades of searching for atmospheres around rocky planets, we were always looking for the same kind of atmosphere, a hydrogen-rich atmosphere, the primordial atmosphere left over from the planet's original formation. And we were always looking for it with the same kind of instrument, the NIRISS and near-spec spectrographs on the James Webb Space Telescope, which were designed and optimized to measure best exactly the wavelength range where hydrogen leaves its signature. But there is another wavelength range that we had never used on rocky planets in the habitable zone, the near-infrared helium line at 10,830 angstroms. That technique had only been applied to gas giant planets like WASP-107b or HAT-P11b, because helium escaping from a giant planet is usually strong enough to be easy to measure. No one had ever pointed it at a rocky planet around a red dwarf. Perhaps we had been looking for the wrong kind of atmosphere for nearly 20 years. Perhaps there is a secondary atmosphere, generated slowly by geological activity inside the planet, rather than left over from when the planet formed, that we had completely missed. That suspicion existed only in a few small groups at Harvard and Carnegie, and few people took it seriously. In other words, most of what the scientific community believed for nearly 20 years was built on a type of observation that was never designed to see the very thing that needed to be found, which makes what is about to happen all the more remarkable. In April of 2017, an astronomer named Jason Dittman and his team in the Mirth project announced the discovery of a new planet transiting a star 48 light-years away in the constellation Cetus, and they named it LHS 1140b. The name initially sounds rather dry, but it actually tells us something interesting. The three letters LHS stand for the Light in Half-Second Catalog, a classic catalog of stars that move across our sky faster than half an arcsecond per year as seen from Earth. In other words, LHS 1140 is not a star standing still in our region of the Milky Way, but a star that is sliding past us relatively quickly compared with most other stars in astronomical catalogs. The star LHS 1140 itself is an M4.5V red dwarf, and here we step into the most important detail of this story. The entire stellar system is about 6 billion years old, which means it is older than our solar system by about 1,400,000,000 years. And this host star rotates on its axis extremely slowly. A complete rotation takes 130 Earth days, more than 5 times slower than our Sun. In stellar physics, rotation rate is what directly generates the magnetic field, and a slowly rotating star means a star with a weak magnetic field, and a star with a weak magnetic field means a star that has not been erupting violently for billions of years. This is precisely the key difference between LHS 1140 and the TRAPPIST-1 system we just discussed. The problem is not that the planets are different, the problem is that the star itself is different. An old, quiet, slowly rotating red dwarf is a rare opportunity that allows a planetary atmosphere to survive. As for LHS 1140b itself, this is a world with a radius 1.73 times that of Earth, a mass 5.6 times Earth's, completing one orbit in 24.7 days, with an equilibrium temperature if there is no atmosphere of negative 47 degrees Celsius, and it sits precisely in the habitable zone of its host star. In 2024, 2 research teams successively pointed the James Webb Space Telescope at this planet. Cadu's team used the nearest instrument and ruled out the possibility of a dense hydrogen atmosphere with confidence exceeding 10 sigma. Damiano's team used the NIRSPEC instrument and reached the same conclusion. What is remarkable is that both independent research teams, using different instruments, arrived at the same conclusion that hydrogen is not the answer. At the same time, revised measurements of the planet's density produced a number lower than expected, low enough to suggest that the internal structure of LHS 1140b may contain a vast amount of water, and the community began calling it a potential water world. If there is an atmosphere here, it must be a secondary atmosphere, thin, composed of heavier molecules, such as nitrogen or carbon dioxide, generated slowly by geological activity inside the planet rather than from a primordial gas envelope. But no one had measured it. Yet the most important question, the question the entire exoplanet field had been waiting 20 years to answer, whether this planet actually has an atmosphere, still had no direct answer. Answering that question required a different kind of tool from what the community had relied on for nearly a decade. What makes the James Webb Space Telescope powerful is that it does not need to fly close to any planet. JWST does not take pictures. It reads the light itself, splitting that light into individual wavelengths to reveal the chemical fingerprints of whatever it is looking at. Pointed at a faint point of light tens of light years away, it can tell researchers which molecules are present, what the temperatures of different atmospheric layers are like, and how that atmosphere is behaving over time. But there is one gas, helium, that leaves its signature only in a very narrow wavelength band in the near-infrared around 10,830 angstroms, which JWST is not optimized to measure for small rocky planets. That is when another tool entered the picture. That tool is a spectrograph called WINARD, originally designed and built by engineers at Kyoto Sangyo University in Japan, then mounted on the 6.5-meter Magellan Clay Telescope at Las Campanas Observatory in Chile, a ground-based telescope, not a space telescope. The special power of WINARD is its ability to measure precisely the helium line that JWST misses at extremely high resolution. Until this year, this technique had only been applied to gas giant planets, places where escaping helium is easy to measure. No one had ever pointed it at a rocky planet around a red dwarf in the habitable zone, and what is happening here is a rather special scene. Humanity is closing in on LHS 1140b from 2 directions at once. JWST from space has already ruled out a dense hydrogen atmosphere, and now Magellan Clay from the ground is preparing to search for the helium signature. 2 instruments in parallel from 2 different hemispheres of science surrounding one planet. And here there is a second, quieter flip that is no less important than the flip about red dwarfs. This is the first time in history that an atmosphere on a rocky planet in the habitable zone has been confirmed, and it did not come from a billion-dollar space telescope, but from a ground-based telescope fitted with a Japanese instrument. This flips a second assumption, not only about red dwarfs, but about tools. We do not always need JWST to do historic science. If you're the kind of person who wants space stories explained clearly instead of buried under technical jargon, hit the like button on this video right now, because that really helps this kind of content reach more people who will enjoy it. The first major discovery revolves around a name that until recently very few people outside the astrophysics community had ever heard. In 2025, a doctoral student at Harvard University named Colin Cherubim, together with his second advisor Robin Wordsworth, published a theoretical model that at first hearing seemed almost contrary to what the community had believed. Their model takes in a series of measured parameters about a planet, its mass, radius, density, surface gravity, the age of the stellar system, orbital period, and the intensity of X-rays the host star is pouring out, and then calculates what the upper atmosphere of that planet must look like after billions of years of being eroded by radiation. Cherubim named the mechanism he described atmospheric fractionation. The core idea is subtle. Over billions of years, intense radiation from the host star continuously heats the upper atmosphere of the planet. The lightest gases, primarily hydrogen, reach escape velocity and fly completely into space, lost forever. But helium, although also a light gas, needs a little more energy to escape than hydrogen does. The result, after a few billion years, is a planet that has almost completely lost its hydrogen, but retains helium at an unusually high concentration, and this is precisely the characteristic fingerprint of a planet that has aged in radiation. Cherubim and Wordsworth's paper listed 30 candidates across the entire exoplanet community that the model predicted should carry this fingerprint. And two of the highest priority targets both happened to orbit the same star, LHS 1140. At the time, the idea struck many of Cherubim's colleagues as hard to believe, and no one had yet pointed the appropriate instrument at a rocky planet in this way to test whether it was real. Even Cherubim's primary advisor, David Charbonneau, one of the most influential astronomers in the exoplanet field of an entire generation, was initially skeptical. The approach was too radical. No one had ever done this for a rocky planet. But Cherubim persisted in requesting observing time on the Magellan Clay Telescope in Chile. That changed when the observing time was granted. On a southern hemisphere spring night in September of 2024, at Las Campanas Observatory in the arid mountains of northern Chile, the Magellan Clay Telescope was pointed toward the constellation Cetus. In the same window of a few hours that night, both LHS 1140b and its sibling in the system, LHS 1140c, began transiting in front of the host star. The star's light filtered through the edges of the atmospheres of both planets and flowed into the wondered instrument. On the 16th of July of 2026, less than 8 months after the theoretical paper was formally published, the results appeared in the journal Science with the digital object identifier 10.1126/science.aea9708. A clear helium signal was escaping from the upper atmosphere of LHS 1140b, matching almost perfectly what the model had predicted. What is remarkable about this story is its sequence. The formal theoretical paper appeared in 2025, but Cherubim's model had existed before that, early enough for him to use it as the argument for requesting observing time in September of 2024. Theory led the way. Observation only came afterward to confirm. This is a victory of theory over intuition, and one of the rare moments in modern science when a mathematical model accurately predicted something the entire community had believed did not exist. There is a second discovery tied directly to that helium signal itself, and it is quieter than the first discovery, but honestly just as shocking once you sit with it. The first obvious question is why detecting helium escaping from a planet proves that the planet has an atmosphere. The answer lies in a simple but inescapable logic. Without a sufficiently large atmospheric reservoir underneath, there could not be a continuous supply of helium to sustain the escape rate the researchers measured on geological timescales. Cherubim's model calculates that the atmosphere allowing helium to escape at the present rate must already have existed for more than 3 billion years to reach the state we are observing now. But what is remarkable is that this does not merely prove there is an atmosphere. It implies something much further. To understand why, we need to turn to something few people know about our own planet. Helium, although the second most abundant element in the entire universe, is actually extremely rare on Earth. Not because Earth has no helium, but because helium is so light that whenever it appears in the atmosphere it always rises and eventually escapes into space. If Earth had no replenishing source, helium would have vanished from our atmosphere long ago. So where does that source come from? The answer is rather surprising. It comes entirely from underground. Uranium and thorium in the rocks of Earth's crust and mantle, when they decay, emit alpha particles. And an alpha particle, in terms of nuclear physics, is precisely the nucleus of a helium atom. Over millions of years, these newly born helium atoms from radioactive decay slowly accumulate in natural gas deposits. The helium balloon a child blows up at a birthday party comes from underground, not from the air. Applying the same logic to LHS 1140b yields an inescapable inference. If helium is continuously escaping while the atmosphere still exists after 3 billion years, there must be some source continuously replenishing helium from below. The most plausible source is exactly the mechanism operating on Earth. Radioactive decay in the rocky core of the planet, combined with magma activity bringing the newly formed helium atoms to the surface. In other words, LHS 1140b may have an internal structure similar to Earth's at the most fundamental level: a rocky core containing radioactive elements, a circulating magma layer, an atmosphere replenished from below. This is indirect evidence for a planet that is still geologically alive, not a rock that died long ago, a rocky planet with magma beneath, an atmosphere above, and somehow still holding on to both despite the brutality of a red dwarf sitting right beside it. The researchers cautiously suggest that LHS 1140b may once have had a much thicker atmosphere billions of years ago, when the host star was still young and fierce, and what we see today is only the remnant of a much larger atmosphere that has been mostly stripped away. This is not unfamiliar at all. Earth itself once had a carbon dioxide-rich atmosphere with almost no oxygen billions of years ago, and the atmosphere we breathe now is only one evolutionary state in a long sequence of different states. And the question hovering at the end of all these inferences, the question no one wants to say out loud but everyone is quietly asking, is if LHS 1140b has magma, possible liquid water, and an atmosphere, then exactly what else is missing for it to have life? To truly understand what this means, we need to look at the raw numbers directly. The light reaching the surface of LHS 1140b is only 43% of the light reaching Earth, which means midday on that planet would look like a late afternoon here, when the sun has already begun to touch the horizon. The equilibrium temperature of the planet, if there is no atmosphere holding heat, is negative 47 degrees Celsius. Surface gravity reaches 1.87 g, meaning if you stood there, your body would weigh nearly twice the weight you are used to on Earth. The host star itself, LHS 1140, has only 18% of the sun's mass and 21.6% of the sun's radius, with a surface temperature of 3096 degrees Kelvin, which is just a little more than half the surface temperature of our sun. One orbital day, that is a full year on LHS 1140b, lasts 24.7 Earth days. But because the planet sits much closer to its host star than Earth sits to the sun, that host star itself occupies a huge place in the sky, with an angular diameter 5 to 6 times larger than the sun as seen from Earth. And there is one final detail worth pausing on for a moment. Because this is a red dwarf, its peak wavelength lies in the near infrared, which means the human eye would not see most of the energy it emits. The portion of energy visible to our eyes is only a thin band of orange-red, like the leftover glow of the hottest embers on a fire that has just died down. And now comes the third discovery, and this is the one that honestly confuses people the most once it is explained properly. Because the strongest point of the paper Cherubim published in 2026 is not the helium signal on LHS 1140b itself, but an accompanying detail that at first seemed merely coincidental. On the observing night in September of 2024 in Chile, not only did LHS 1140b transit in front of the host star, its sibling in the system, the planet LHS 1140c, also transited the star in the same window of a few hours that night. And LHS 1140c is a very different object. It has a mass 1.91 times Earth's mass, nearly twice our planet, and a radius 1.272 times Earth's, meaning its density is actually higher than Earth's. This is a dense, rocky planet in the literal sense of the word. If you asked which planet in the LHS 1140 system is more Earth-like in terms of rocky structure, the clear answer is C, not B. But LHS 1140c sits much closer to the host star, 3.5 times closer than B, and is receiving about 12 times more radiation than planet B. What is remarkable here is the method. Both planets transited the host star on the same night, same instrument, same analysts. Only one single variable differed, and the result differed in only one single point. For LHS 1140c, there was no helium signal at all, no atmosphere. This is the dream scenario no scientist dared hope for, a perfect control experiment in which the only differing variable is orbital position. It rules out every alternative explanation one could invent. It cannot be an instrumental artifact, because that same instrument produced a clear signal on planet B. It cannot be system noise, cannot be variability in the host star's activity, cannot be an analysis error. This turns the helium signal on LHS 1140b into a physical reality, not a statistical hope. And there is a deeper paradox glittering underneath this entire story. Because LHS 1140c is the more genuinely rocky planet than B, denser, with a more solidly rocky structure. If someone had to bet beforehand on which planet in this system was more likely to retain an atmosphere, all the old rules would have pointed towards C. But reality is completely the opposite. C is bare, B has an atmosphere. This makes the flip even harder to swallow. At the same time, LHS 1140c itself reinforces the correct part of the old dogma. A rocky planet too close to a red dwarf really does get its atmosphere stripped bare, exactly as every model has predicted for 20 years. But LHS 1140b, sitting at a distance just far enough away, has broken that dogma. The inescapable conclusion from this single observing night is that there exists a certain distance range around every red dwarf where a rocky planet can retain its atmosphere. The habitable zone of an M star, the thing the community had quietly buried for nearly 2 decades as an illusion, suddenly becomes a region that needs to be surveyed seriously again. The entire field of exoplanet research just shifted in a single observing night. If you find this as strange and captivating as I did when researching it, leave a comment and let me know, because that really helps me decide which space stories are worth doing next. Now, for a moment, picture what you would actually experience standing on the surface of LHS 1140b, because the details are almost impossible to imagine any other way. The first thing that would hit your eyes would be the sky. The host star is not a small bright point like a coin hanging high the way our sun is. It is a gigantic orange-red sphere occupying a significant portion of the dome of the sky, a large disk like a full moon slowly burning and hanging motionless right above your head. But redder, dimmer, warmer, like a sunset that has frozen permanently and has no intention of turning into night. There would be no midday in the sense you are used to, only a certain kind of orange sunlight, always at the same angle in the sky, not moving from east to west. The reason is that LHS 1140b is very likely tidally locked, the phenomenon in which a planet rotates on its axis at the same rate as its orbital period, so that one face forever points toward the host star and becomes the day side forever, while the other face forever turns its back and sinks into darkness forever. Between those two faces there is a narrow transition strip that scientists call the terminator zone, where day and night meet in an endless twilight, where temperatures can be just right, where winds constantly blow from the day side to the night side carrying moisture. That may be the narrowest and perhaps the only strip on this planet where life could exist, but the most immediate sensation you would notice is not the sky, but your own body. You would feel so heavy that every step would be like wading through mud. Not mud in the sense of slow wading, but every time you try to lift your foot, some force is pulling it down harder than ever. Joints and bones would have to work twice as hard as normal. The heart would beat faster. Your breathing would be heavier. Just standing still would already be a form of exertion. If the water world hypothesis is correct, beneath your feet there could be an ocean hundreds of kilometers deep, hidden under a thick ice shell, or in the Terminator region there could be an open ocean with clouds, with rain, even with slow-moving waves under the red light. Or perhaps everything beneath you is an ocean that froze long ago and will never thaw again. And the light here, this red light, is unlike any light humans have ever seen. There is no blue in it at all, only bands of orange, red, and infrared. If somehow there were plants here, they could not photosynthesize with green chlorophyll the way Earth's plants do. They would need completely different pigments capable of absorbing infrared light and red wavelengths, which means they might be completely black or deep purple, not green. A forest, if it existed here, would look like a dark field stretched out under a red sky, and the night sky, or rather what on the day hemisphere you might call the sky, would have no other stars bright enough to see. The orange-red light of the host star would drown out everything behind it. True night would exist only on the opposite face, where temperatures could drop below negative 150 degrees Celsius, and there would be nothing but cold darkness lasting forever. If you looked straight up at the sky, you would not see with your eyes what is happening high above, but it is still happening right now. At an altitude of about 200 kilometers above your head, helium atoms from the upper atmosphere are quietly drifting out into space. A little every second, without pause. The strangest feeling is that you are standing on a planet receiving enough light that in theory it could harbor life, but that light is unlike any light humans have ever known. 3 billion years. That is the length of time everything you have just imagined has already been existing like this. That is a span longer than the time-complex life has existed on our own Earth. Our multicellular life is only about 600 million years old. If LHS 1140b has any form of biology, it has had nearly 5 times as long as Earth to evolve, long enough for microbes to appear. Long enough for multicellular organisms, and long enough, perhaps, for things we have not even imagined. But there is still a great deal we do not know about LHS 1140b. The first mystery is the detailed composition of the lower atmosphere, which may contain water, carbon dioxide, or nitrogen that a joint program between the James Webb Space Telescope and the Hubble Space Telescope will spend the next 4 to 5 years searching for. The second mystery is whether this is truly a water world, when density measurements suggest that 9 to 19% of the planet's mass could be water, and if so, this would be one of the largest oceans ever measured on an exoplanet. Whether that water is liquid or frozen, no one yet knows, but with a heat-retaining atmosphere and magma below, liquid water in the Terminator Strip is entirely plausible. The greatest mystery, of course, is whether there is biology, and the answer will need another decade through biomarker spectral signatures. There is a subtler mystery that has quietly been causing debate. When Cherubim's team returned to observe in 2025, the helium signal disappeared. Not that the atmosphere disappeared, but more likely the helium is only detectable when in an excited state, a state that depends on the magnetic activity of the host star. And the deepest theoretical mystery is the Fulton Gap, a strange void in exoplanet statistics at radii of about 1.5 to 2 times Earth's, where LHS 1140b sits precisely in the middle. The favored hypothesis is that planets falling into this range are mini-Neptunes in the process of losing their gaseous envelopes and gradually turning into rocky super-Earths. LHS 1140b may be a living image of exactly that transformation process, caught right in the middle. And finally, 48 light-years. No mission ever built could reach it. But we do not need to go. We read LHS 1140b through spectra, and we are doing exactly that, steadily, year after year. This is the detail that tends to linger longest in people's minds after hearing the entire story. Red dwarfs make up about 75% of every star in the Milky Way, that is about 200 billion out of a total of 250 billion stars. Until this week, the community believed that the habitable zone of all those stars carried no serious biological meaning. Now, just one planet, LHS 1140b, has proven that an atmosphere can survive more than 3 billion years beside a red dwarf, and that entire assumption must be rewritten. Cherubim listed 30 similar candidates among only the planets we already know, and there may be tens of billions of other rocky planets around red dwarfs also holding atmospheres in the same way that we have never looked at. The habitable zone of an M star has just become a region that needs urgent surveying, and there is one detail about the lifespan of these stars that makes everything even more astonishing. Red dwarfs are only extremely active for about the first 1 to 2 billion years of their lives. After that, they quiet down and remain stable for thousands of billions of years, more than 100 times longer than the current age of the entire universe. They can do that because they are fully convective stars, able to circulate their entire mass through the core and burn nearly 100% of the hydrogen they have. Sun-like stars cannot do that. That means if a planet survives the violent youth of its host star, it can be nourished by that star 1,000 times longer than the time Earth has had life. And Cherubim has proposed a name for the class of planets that LHS 1140b belongs to. He calls them helium worlds, planets that have lost nearly all their hydrogen but still retain helium. If LHS 1140b is the first specimen of this class, we may soon have to rewrite the textbooks on exoplanet classification, adding an entirely new type. So what does all of this ultimately mean? It means the dogma about red dwarfs has been broken by a planet that has been bleeding helium for the 2 decades that science believed it was impossible. The question now is no longer whether rocky planets in the habitable zones of red dwarfs can retain atmospheres. The answer is yes, at least one has done it. The question now is how many others are doing exactly that right now that we have not yet looked at. LHS 1140b is not a second Earth. It is nearly 6 times heavier than Earth. Its atmosphere is helium-rich rather than nitrogen. Its gravity is double. It orbits an old red star. But it has done what for 2 decades we believed was impossible. And once something impossible has happened, every old assumption must be re-examined from the beginning. The question is no longer whether it is possible. The question now is where else? If stories like this one, based on genuinely published research rather than hyped headlines, are what you want to see more of, subscribe to the channel and turn on notifications because the James Webb Space Telescope and Magellan Clay are still returning to LHS 1140b month after month, and the next data cycle may very well add another strange piece to this puzzle. Thank you for watching, and I will see you in the next video.